So please give a very warm welcome to Alistair Smith.
Thanks very much. Thanks everyone for coming. I recognise some faces in the audience, so those of you who know the company well might want to dig into a bit more technical detail. I'm very happy to do that in the interval after the second speaker. I'm going to keep this talk relatively introductory for those of you new to the company, so that's the kind of balance. So as we said, the company is focused on cancer immunotherapy. I thought it was worth just spending 2 minutes just giving the background to cancer immunotherapy, but more importantly than that, explaining where the shortcomings in cancer immunotherapy currently are, because that's the gap in the clinical need that we want to address, because that's where the significant clinical benefit is coming from, and therefore, frankly, the commercial value. So let me just sort of first of all introduce the whole space of cancer immunotherapy. Cancer immunotherapy is about harnessing the immune system to attack cancer in simple terms. So the immune system, the human immune system, is more than capable of having a very positive effect in fighting cancer. But there are ways in which cancers have evolved to avoid the immune system, and that's the challenge that we need to get over. So just to talk briefly about some successes, and there are lots, so I've just picked out one very much in the public domain. A lady called Sandra Sace, who is a while ago now, 13 years ago, was in a very poorly way, with only months to live, stage 4 melanoma, and she was part of an early. Sorry, Shelley's pointing. Shall I move all the way over there? I can't click the thing, I've got to push the laptop button. So she was in a very poorly way. She was part of a trial of a very early immunotherapy targeting something called CTLA-4. And the long story short is that was extremely successful, and she's still very healthy and in complete remission. So there are some stunning success stories around immunotherapy. And since about 1997, when the first monoclonal antibody was approved in this immunotherapy space, and you'll see a thing here, these are all monoclonal antibody therapies. And just to touch on the introductory point, that we have a technology which we call Affimers, which are an alternative to monoclonal antibodies with a number of commercial and technical benefits over that platform. But just to see, since 1997, a number of monoclonal antibodies approved, including ipilimumab, which was the CTLA-4 drug that Sandra was treated with, through to things like Keytruda, which is probably the largest selling immunotherapy now, someone can correct me if I'm wrong. But there have been 75 immunotherapies approved over time, to my reckoning anyway, and 15 of those in the last year. So this is a very hot area of drug development. There is a huge amount of interest in large pharma and large biotech in these types of drug assets. There is considerable M&A licensing deals done in this space. It's a very hot area because of the successes that we've seen. Okay, so one more introductory slide on what is immunotherapy. So again, in simple terms, when your immune system, I'm using an immune cell to illustrate that here, when your immune system comes into contact with a tumour cell, ideally what you would like is an attack on that tumour cell. When your immune system comes into contact with a healthy cell, you don't want that to happen. So there are signals that are passed between healthy cells and immune cells to say, leave me alone, don't attack me, I'm a healthy cell. And what has, through evolution, those signals, which all have different names, some of you will recognise these signals have been adopted by the cancer cells, and the complementary signals are used to tell the immune system, I'm a healthy cell, leave me alone. So it's a way of hiding from the immune system that is the problem. So if you can develop drugs which block those signals, one just not working out. If you can block those signals, then you can switch off that ability to evade the immune system, that invisibility, you can switch that off and the immune system will attack the tumour cell. So it's all about controlling these immunology signals to allow the immune system to do its job. Okay, so those are the introductory slides, and here's the challenge. So the data on the left is from Pfizer, it's sort of in the public domain. It's very well known now that only really on average about 20% of patients respond to these types of immunotherapies. So 70 to 80% of patients do not respond. Those who do respond very well. You obviously get massive improvement in terms of clinical outcome. But 70 to 80% don't respond very well at all. And part of the reason for that is shown in these two panels on the right. So the 20% where you see the brown staining there in the biopsy, that's the immune system that is already in the tumour, in the cancer, not doing anything necessarily yet. But when you treat them with immunotherapies, that helps the immune system, and because it's already there, it will have a positive effect and you get clinical benefit. For those patients, the 70 to 80% where there's no immune system in the tumour, you don't get that response. There's no immune system to help with your drug. So there is no response for those patients. So that is the real challenge. And again, to be frank, that's the commercial opportunity. The clinical benefit you could bring to those patients who don't respond to these types of therapies is enormous. And there's obviously some understanding growing now about how you would do that. So, our job as a drug developer is to improve patient survival. For those patients on the left who already have what's called an immune infiltrate into the tumour, then one of the things that's now known to be very successful is to treat the patient with more than one immunotherapy at once. Okay, so you get an incremental benefit by treating with more than one immunotherapy. So that's one thing you can do. In terms of those patients who have no immune infiltrate into the tumour, they're called cold tumours on the right and hot tumours on the left. So cold tumours, one of the things that's now known, if you treat with chemotherapy, and it starts to kill cancer cells as well as cells all over your body, unfortunately. But killing the cancer cells creates an inflammatory response, it creates an immune response, and that will draw the immune system into the tumour. So chemotherapy will turn the cold tumour to some extent into a hot tumour, and then your immunotherapy will start to work. So that sort of combination of chemotherapy and immunotherapy is becoming standard of care in some cases. But of course, the only thing that's available to drug companies at the moment is a chemotherapy, which, given to a patient systemically, has all the side effects: heart, liver, kidney being damaged, loss of hair, and so on. Chemotherapy plus a separate immunotherapy. And that's where we have something really unique that can make a big clinical difference to these patients. I'll come to that in a second. So if you look at both of those approaches, first of all, if you want to give patients two antibodies, that's very expensive. So a monoclonal antibody treatment is around $150,000 per patient per year. So if you want to improve their outcome and give them two at once, or even three at once, then you're talking enormous cost, which payers around the world are balking at for understandable reasons. So antibody therapy is very expensive. That limits what you can do. Hitting more than one drug target with a single antibody is really quite challenging. And antibodies are big molecules, so they don't penetrate solid tumours as well as you would like them to. So what we have developed internally and through our collaboration with Tufts University, which is the medical school at Tufts University, which is one of the top few in the US, these two platforms, the Avacta platform and the TMAC platform, which I'll talk through very briefly, and then go on to talk about our milestones that are coming up over the next few months, as we said earlier in the introduction, that really could catalyse some significant increase in value for the company. So the Avacta platform is, as I said earlier, an alternative to antibodies. So this is a smaller therapeutic protein, so it does the same job as an antibody. It can recognise a target and block it, or in fact recognise a target and stimulate it, if that's what you want to do. But it's a lot smaller than antibody. Remember, antibodies are big, so solid tumour penetration is not as good as you would like. These are 10 times smaller than antibodies, so better tissue penetration. They are extremely simple proteins compared to antibodies, and that translates into their manufacturing being a lot cheaper and simpler, but also translates into the fact that you can make more clinically interesting structures to hit 2 drug targets at once or 3 drug targets at once, because we can do that as a much simpler protein, and we'll talk about that. So the Avacta platform is an alternative to antibodies that allows us to build clinically better immunotherapies than you can necessarily do with antibodies. The TMAC platform is a slightly, boring name, but the TMAC platform is all around targeted chemotherapy. So what we have exclusively licensed from Tufts, so both of these platforms are totally proprietary to Avacta, so the access that other people, partners like LG and Moderna have, is through licensing with us. The TMAC platform allows us to target chemotherapy specifically to the tumour. So remember we said that the systemic exposure of the whole body to chemotherapy has all sorts of side effects that we're all aware of. Some of them very serious in terms of cardiotox or hepatotox, liver tox, that limit how much chemotherapy you can give or how long you can give it for. So what our TMAC platform allows us to do is target that chemotherapy so that it is only activated in the tumour and you don't get the systemic exposure. So that clearly allows you to reduce the side effects, potentially give more of the chemotherapy, or perhaps more importantly, give it over a longer duration, which is more beneficial to patients. So really just a pictorial reiteration of what's on the previous slide. You can see an antibody there is a big, complicated molecule actually made up of several subunits that are held together. So it's a complex thing to develop and to manufacture. And Avacta is really, protein 101. It is a very, very simple protein, 10 times smaller, a lot cheaper to manufacture, a lot cheaper to develop actually, and much easier to modify. So that's the first platform. And the second one, obviously the question that immediately arises, well, how on earth do you target the chemotherapy to the tumour? Because you're giving it to the patient, so it's going into their bloodstream. How is it targeted to the tumour? So there's 2 mechanisms for this. The important one here is what we've licensed from Tufts. And that is developed at Tufts. They have a little bit of chemistry, which we don't need to look into the detail of, but I'm happy to describe it later. A little bit of chemistry which stops the chemo from going into cells. So the way chemo works is it gets into cells and it kills the cell from the inside, healthy or cancer. The little bit of chemistry that Tufts have developed stops the chemotherapy from getting into cells. So it renders it inert and inactive. Now that little bit of chemistry gets clipped off when the chemotherapy goes into a tumour, because there's a particular enzyme in solid tumours which is not present or present in extremely low levels in healthy tissue, but at very high levels in a tumour. So there's a little enzyme which clips off that chemistry and the chemotherapy suddenly becomes active, but only in the tumour. So you can give a patient, and we have a lot of that, again, this is not a technical presentation, so the data's not here, but we have a lot of animal data to show this working extremely well in mice and dogs, which are a good translational model for humans, to the extent that in mice we can go to 6 times the normal tolerated dose of a particular chemotherapy in mice. And when you look at how much of that is in the tumour compared to the heart, it's 20 times higher in the tumour than it is in the heart. So there's a strong focusing of the chemotherapy into the tumour and away from healthy tissues. So what that allows us to do, as a company that has two technologies here, is combine the chemotherapy, remember to turn the cold tumour hot, and combine that with the immunotherapy, all proprietary to us. And through that chemotherapy, we don't give the same systemic exposure. So we can give that chemotherapy as a separate thing from the aftermath immunotherapy, with improved clinical outcomes we expect and better safety. Or you can give it as what's called a drug conjugate. Sorry, am I standing in your way all the time? As a drug conjugate, where these two things are physically linked into a single molecule. There are sometimes benefits to that, and sometimes it's better to give as a combination therapy. We can do both of these things with proprietary platforms on both sides. And that's really, if you take my right back to the start, that's what gives you the clinical benefit for patients. Turn the cold tumour hot, and then as the immune system comes in, support it with the immunotherapy. So we're uniquely placed to be able to address those. So a little bit more detail. Our first program, our first AFMA program, which will go into the clinic IND filing at the back end of next year, so about 18 months or so away, and dose first patient shortly after, is around, you'll have seen earlier, the PD-1 immunotherapy target. So our lead program is around the PD-L1 inhibitor to affect that pathway. We're also developing what's called a bispecific. So that's two affiners that hit two different targets in a single molecule, and they're hitting PD-L1 and another target called LAG3. Okay, so there are only two molecules in the clinic, one with F-star and one with macrogenics that hit those two targets. We will be the third into the clinic, so quite a novel bispecific. But then, as I said, the thing to really create value is combining the chemotherapy, and then we have other programs around the drug conjugate that we're developing, PD-L1 with a particular chemotherapy that we, again, own exclusively, bispecific with a chemotherapy, and the combination therapy. So that set of programs on the right is what really gets large pharma, large biotech excited when we talk to them about what Avacta is doing. Okay, not just creating bispecifics and trispecifics that copy effectively what antibodies can do, but these completely different approaches that benefit a much broader range of patients. Then to just come on to that major value catalyst that was talked about in the introduction. So what we've learned recently is that not only as part of that drug conjugate where the chemotherapy is attached to the aftermath, but on its own, the little bit of chemistry we've licensed from Tufts stops the chemotherapy going into the cancer, into any cell. It only gets clipped off in the tumour, giving that release of the chemotherapy specifically in the tumour. Now that's worked, as I said, extremely well in mice and dogs. If we can reproduce that data in human phase 1 clinical trials in the first half of next year, and we're going to do that with a chemotherapy called doxorubicin, which is a very well known, very well understood standard of care in breast cancer and other soft tissue sarcomas. If we can reproduce that in human and see the same increase in levels in the cancer cells and not in the heart, for example, and doxorubicin has quite bad cardiotox side effects, so a lot of patients aren't eligible to get doxorubicin because of that cardiotox. If we can show that we get better safety in humans, then that is a significant licensing opportunity for us. Of course, it will feed into our own immunotherapy, chemotherapy program, so that's important, but as a standalone, it is a potentially very valuable licensing opportunity. And the Tufts chemistry can be attached to any chemotherapy, not just doxorubicin. It's across the board. So there's a whole range of at least 20 different chemotherapies you could imagine. The most valuable being blockbuster billion-dollar drugs. So potentially a very significant value inflection point in the first half of next year, 2020, around this TMAC program. So just to I guess, underscore what I've been trying to say about combining the chemotherapy and immunotherapy. So this, it's a little animation, but it sort of illustrates it well. The immune cell, your immune system is constantly looking over tissues, healthy tissues and diseased tissues. And here the cancer cell in the middle, which you can sort of just make out, completely gets missed because it's displaying the same safety signals as the healthy tissue. So the whole concept of our therapies is to bring in a chemotherapy using an aphamer. The aphamer being an immunotherapy, so it starts to block those signalling pathways. But then only in the cancer is that chemotherapy released, and it turns the cold tumour cells hot, which recruits the immune system, and the aphamer stays there to support the immune system as it starts to do its work. That is a completely novel approach as far as we're aware, and one which I think is going to generate a huge amount of commercial interest, and not least because of these two boxes here. So from an existing market perspective, i.e. patients who are treated with PD-1 inhibitors, for example, there's going to be around 350,000 patients a year, we think, treated with those types of immunotherapies. Now, yet another PD-1 inhibitor on its own is not going to compete in that market. There's several approved already. Keytruda is by far the largest market share. But obviously, combined with chemotherapy, there is an opportunity to compete in that market. But I think more important, as we've said, is the 70 to 80% of patients on the right-hand side, the market expansion opportunity. And if you just look at the number of patients per year, getting on for 2 million in North America and Europe with a range of different cancers, if 70% of those don't normally get treated with an immunotherapy, but would get treated with an aphamer drug conjugate, for example, that opens up an enormous market. 1% of that market is a blockbuster drug. So the commercial opportunity here is huge, as well as the clinical benefit to patients. And the last couple of slides, just to reiterate that point about news flow and significant news flow around IND filing in our main program and dosing first patients with an aphamer, which of course is a huge de-risking point for any potential partner. So that immediately makes doing commercially large licensing deals a lot more straightforward. Through to getting that phase 1 data next year for the prodoxorubicin, the safer form of chemotherapy, through to selecting our clinical candidates for development in other programs. There's a huge amount of technical progress to be made, and clinical progress, but also alongside that, you wouldn't be surprised to know that we're pushing forward with business development efforts, so I wouldn't be surprised to see further commercial deals signed in the next 12 months as well. Really just a summary slide then. We're very confident now, after a few years of developing these molecules, to say this is a best-in-class therapeutic platform. The aphamer is a best-in-class therapeutic platform. But what we're now able to do on top of that is really create a differentiated and wholly owned pipeline of drugs through the combination with a novel chemotherapy with the immunotherapy. That's key to the value going forwards. So lots of near-term value inflection points, clinical, preclinical, commercial. Already got those deals in place with LG, which was a significant deal. That was a few $1 million up front and $300 million in potential earn-out over the clinical development stages. Moderna this year, earlier on this year, executed one of their commercial options to take some customers into their development programs. So another strong validation of the technology. No time to talk about it today, although happy in the interval. We're also building a revenue stream around the diagnostic and research uses of aphamer, so a completely separate market, a different set of people in a different business unit, but a revenue stream, an early revenue stream that's growing quite well this year. Based in Cambridge, just the name. Any questions?
De-risking the first half of next year.
Yep.
With respect to the other parts of the portfolio, don't you think it will be along the line of attracting some patients?
Yeah, so realistically, I think you have to expect that significant licensing deals for aphamer therapeutics are done when they are in the clinic. That's not to say you can't do preclinical licensing deals. We've just done one with LG, which is quite a good one. But if you look at the history of any of these types of technologies, pre-clinically, a few $1 million up front with decent earn-out is the way they share the risk with you. Once you're in the clinic with human data to show that it's safe as a platform, you can expect to put a zero on those upfront payments. And that's obviously where we would like to get to when we start to do deals with, I assume, in Western majors. I think the risk appetite is probably higher at the moment in Asia than it is in the West, because there's a lot of innovative drug development being done in Asia and there's some catching up to do. So a lot of Asian pharma have a greater risk appetite, and it wouldn't surprise me if the next deals are also in Asia.
Any more questions?
Who's your nearest competitor in your area, and how do you differentiate yourself with them, and how have they been successfully delivering your program?
So competitors, I mean, we could take a long time talking about competitors because, first of all, you could look at competitors who have alternative therapeutic platforms. So an obvious one to talk about is Avacta. Some of you will know Avacta. They are a Belgian-based company, been around a lot longer than we have had an alternative therapeutic platform, got bought by Sanofi last year for $5 billion. So I think in terms of a technology comparator, Avacta are a close fit. But I think comparators in general, because of what we're doing around the drug conjugate approach, you have to start thinking about other drug conjugate companies, and perhaps at the interval we can talk about those. I can't remember the third point from there. Oh, what we're doing is different. I hoped I got that across. But the thing that we are doing that is different is we have a way of unlocking treatments for those patients in the 70 to 80% with the combination of chemotherapy and immunotherapy, but with a much safer chemotherapy. So you don't get the same systemic exposure to the chemo and the same side effects. So that is what I believe completely differentiates us from anybody else in this field.
How much cash have you got, and what's the cash burn?
So balance sheet, we've got an interim statement to the end of July, so you can see accurate numbers then. Balance sheet at the moment around £10 million. Cash burn is around £10 million per